Z-scores. In this lecture, we're going to talk all about Z-scores. So the location, what it means to have a standardized distribution. We are going to start talking about the location of a Z-score, how we transform scores, or X, right? The X values into a Z-score, transforming Z-scores into X's, X's into Z-scores. We're going to talk about describing the effects of standardizing a distribution, and then again, transforming scores into standardized distributions. Some of the things to please don't forget about from lecture 3, the mean or average. Yes, when we talk about a population, it's called a mu. Standard deviation from lecture 4, and then all of your basic algebraic notations and equations. Okay, so some introductory points with Z-scores. They do help us identify and describe the location of every single score on a distribution. So when we think distribution, think that normal curve or that normal distribution. Don't think skewness, think perfect symmetry, okay? Z-scores also work really well in a standardized distribution, right? They do help us standardize into an entire distribution. They take different distributions and they make them equatable to each other, right? Equivalent, comparable. So I can take a look at how Martha does in her English class and how Zachary does in his German class, right? And I can say who has the higher score. Yes, we're talking about two different people in two different classes, but if I can standardize it, or I can take a look at their raw scores, transform them into Z-scores, I can say which one has a higher score. I can compare them. And then Z-scores are also called standardized scores. So take a look at these two different distributions, right? So again, nothing is changing with how we look at graphs. So the height of the blocks, if you will, the height of those bars, right, is the frequency. So you can see that, okay, in our first table there, our first distribution graph, we have, 5 people that had a score of 19, and we had 3 people that had a score of 18, right? So that frequency, that F, is still how high it is, corresponds to the frequency. And then the X, the horizontal, the right to left one, right, is the scores, the X's. Okay, so for both distributions, the mean is 20, right? So in the A and B one, right, so you can see mean is 20, mean is 20. The average score was 20 for both, okay? In the first distribution, though, the standard deviation was 2. And the second distribution, standard deviation was 10. So crazy variability all over the place, right? And you can see that with the distribution of scores, right? So remember how in last lecture we talked about variation or variability, how spread out, how all over the place the scores are versus how tightly clustered they are, right? So in A, you see how you have that one outlier of 26, right? But most of the scores are really tightly clustered together. So in both distributions, you have an average score, a mean or a mu of 20. And in A, you have a standard deviation of 2, which indicates a tightness of, or close clustering, right, of your scores. And you can see that a lot of people scored a 19, a lot of people scored an 18, a lot of people scored a 20, 21. No one really scored an 8 or a 10 or a 33. You did have that one person that was like a 26, and we'll call that you, right? That's your score. Okay, if you look at B, same thing. You have an average score of 20. But now look at the scores. You had 2 that scored an 8, and 1 that scored a 9, 1 scored a 10, 3 that scored 11. Nobody scored a 12, 13, 14, 15, 16. One person scored a 17. No one now at this point scored the average of 20. No one even got close to the 20. No one scored an 18, 19, 20, 21, 22, 23, 24. Yes, you still scored the 26. But now because that standard deviation, that measure of variability, again, because we get standard deviation from variance, right? Just take the square root of variance and you get standard deviation, is 10 or 5 times greater variability in B versus A. You now have people scoring higher than you. Now you have 3 people scoring a 28, and 1 person scoring a 30, and 2 people scoring a 31, and 1 person even got the maximum of 33. Okay, so your score of 26, the relative position is now sliding, right, compared to the mean. It's very different in these two distributions. Okay, so say you are really good at chemistry. Okay, A might be how the scores in that, I don't know, final exam kind of ended up, right? So this is everybody in the class, and chemistry is just a tough class, right? So the highest score was a 33. Nobody scored it, and you're like, oh man, I didn't do that well. I got 26 out of 33. Well, actually, you did really well. You scored the highest score by far. The average score was 20. The closest person to you was 22. You scored the highest score. But maybe you kind of struggle with, I don't know, your foreign language class, okay? If the professor says, yeah, the average score was still 20, and you scored a 26, you might walk away from that final thinking, okay, I did pretty well, right? The average score was 20 in the class. I scored a 26. Relative position, though, what does the professor think about your skills, think about your ability in the chemistry class versus in that foreign language class? My money is that the chemistry professor thinks that you're a rock star, right? The chemistry professor in A, example A, right? They're like, this is just a really tough class. The material, the concepts, the topics that we talked about, it's just hardcore, right? And man, the average score was 20, and for whatever reason, this kid scored 26. Good job, them. Okay, z-scores and locations in distribution. So the nice thing about, or the most powerful thing about z-scores is that it gives you the exact location of a score within that distribution. Okay, so just like I have an exact score, 97% or 97 or 14 or 13 or whatever it is, right? I can have an exact location on a distribution with a z-score. Okay, so a z-score has two things. It has a sign and it has a number. The sign tells me, am I above the mean or below the mean? So if I have a positive z-score, a positive number z-score, I know that my raw score, whatever that was, is above the mean. Now, again, please keep in mind, positive does not mean good, negative does not mean bad. It just means that that raw score is above the mean. A negative score is below the mean. Meaning, if I have a raw score of 14 and the average is 16, I have a negative z-score, okay? Depending on what the standard deviation is, that kind of stuff. Z-scores are usually going to fall between 0 being perfectly average, right? And 4. Yes, they go on to infinity, but realistically, you're never really going to see one above plus or minus 3, okay? So the sign tells you, is this z-score, and then by default, is the score above or below the mean? If you're talking about debt, you want to have a negative z-score, right? You want to have less debt than the average person. Below mean or above the mean. And then the number is the distance. How far away from average is it? And again, z-score is going to be a lot smaller. You're going to have a z-score of like positive 0.34. That's okay. Or a z-score of negative 1.2. We're talking very, very small numbers. Okay, so take a look at this. So a couple things I want you to look at with this very big distribution here. Okay, the mean is right down the center, right? Or the mu. Okay, so normal distribution, so perfectly symmetrical. Left-hand side looks just like the right-hand side. Take a look at the very, very bottom part of it first. Okay, you see how at the very, very dead center, very bottom is 0. If your raw score is 76, you got a 76 in the last test, and the average score was 76. You're perfectly average. Your z-score is 0. Okay? So you are the balance point. You are perfectly average, okay? If you are one standard deviation above the mean, so let's say the standard deviation is 10. So you scored a raw score of 86. All right, so average is 76, you score an 86 because standard deviation is 10. So you are one chunk, you are one unit, you are one standard deviation above the mean. Your z-score is 1. And because it's symmetrical, whatever happens on the right-hand side can happen on the left-hand side. So if you scored a 66 on the last test, you are one standard deviation below the mean. And it can keep going both ways, right? So if you scored a 56, you are now 2 standard deviations below the mean. Your z-score is -2. If you scored a 96 and the average score was 76, your z-score is +2 or +2 because you're 2 standard deviations above the mean. Okay, so you see that little like kind of dotted dashy line right there in the middle? That's indicating the very, very dead center. And then you have that kind of, so the red distribution, right? And then you have that kind of like that chunky one, right? In between 0 and 1. What that's indicating is all those scores in between that area there, right? All those scores are all your fellow classmates that scored between a 76, which is the average, and 86. Because they have a z-score between 0 and +1. Okay? Because this is a normal distribution, remember how we talked about tails, right? So the body is the middle part. The tails are the very, very ends. Right, think back to your skewness, right? So like the body is like the big elephant and the tail, which way is the tail pointing, right? If it's pointing towards the positive end of the number line, it's positively skewed. If it's pointing towards the negative end of the number line, it's negatively skewed. Same name or terms here. Now the body's in the middle, and the tails, we have 2 tails. Okay. Notice how the tails taper off really, really tight there towards the end. Okay. Meaning the bulk of the data is now plus and minus 1. Because again, the frequency is how high up does it go. So take a look at this. So if the bulk of your fellow classmates and you fall between plus and minus 1 standard deviations from the mean, right? And even more so of the data falls plus or minus 2 standard deviations from the mean, or if you convert their raw scores to a z-score, they'll have a z-score, most, like 99% of you, will have a z-score between -2 and +2, right? So when we're talking about populations, and we're talking about IQ, we're talking about SAT scores, we're talking about anything to do with things that you can measure on a grand scale. And this also holds true for physiological phenomenon too, things like height and weight and blood pressure and things that occur like physiologically with us, like with our bodies, right? Yes, you do have people that are what we call like outliers, or people that will have like an IQ score or an SAT score that will yield like a z-score of +3 or -3.5. Very, very rare. And remember, keep in mind, a z-score, you can find a z-score for any raw score. Okay, so here's your formula. The numerator, the one that sits on top, right, is the deviation score. How far off from the mean does it deviate? So you take the score, that individual score, from the mean, minus the mean. The denominator, that bottom score, right, expresses the deviation in standard deviation units. Remember your Greek letter, sigma. So it's that circle with a little curlicue on top. Okay, so your population z-score formula is x minus mu divided by sigma. You can also determine a raw score, x, from a z-score. Algebraically, you can solve for x. Now, remember, if you have, in this case, normally I've been saying up until now in the lectures, if you have 2 bits, you can always find the 3rd bit. Now I'm going to say if you have 3 bits, you can find the 4th bit. Okay. So in the previous slide, I said z equals x minus mu divided by sigma. Yes, absolutely. But what if you don't have x, but you have the population mu, like it's well known, you have the z-score for it, you have the sigma or the standard deviation? Can you find the raw score? Yes. You just algebraically flip it around. Okay? So the raw score is simply the population mean plus or minus, if the z is below the mean, z multiplied by the population standard deviation. Again, and I put a little smiley face in there just to make it fun. Just switch the equation around just a little bit. So z equals x minus mean divided by the standard deviation. X can also equal mean plus z times standard deviation. So I'm taking a dividing equation and I'm just flipping it into a multiplication equation. Because if you have 3 of the bits, you can always find that 4th bit. Okay. Most of the time we use z topics, z stories, z problems, right, for populations, but you can use them for samples too. Okay. When you determine a z-score for a sample, you have to do a little bit of accommodations for it. It's not going to give you an exact position on that standard distribution. It's going to give you a relative position, and that's okay. And you know this, right? So in last lecture, we talked about like sampling error, or we introduced the idea of sampling error and a bias that creeps in when you're dealing with a sample. That's okay. Most of the time when you're running an experiment, you're not dealing with a full population. That's totally okay. We know that. We just have to accommodate for it. So it's more going to indicate the distance from the sample mean versus the distance from the population mean. Totally fine. Yes, you can still transform that distribution into z-scores. It's going to retain the same shape as the original distribution and the same mean for a sample mean, again, not the population mean because you're dealing with sample statistics. Okay. I want to touch on just a little bit other relationships between z-scores, x or raw scores, the mean, or if you're dealing with population, mu, and standard deviation, variance, and variability. So a z-score establishes a relationship between the raw score, the mean, and the standard deviation. Absolutely. When given a mean, or average, and you also know the raw score, and therefore you know the z-score, you can compute the standard deviation. Right? So if you're looking for the standard deviation, you can find it as long as you have the mean, the raw score, and the z-score. Also, when you already have the standard deviation, the raw score, and the z-score, you can compute the mean. Okay? So if you come across a homework problem or a test question, and you're like, wait, they're asking me to find the mean. I wasn't told how to find the mean. Yes, you were. You were given the equation, and you know if you have 3 of the bits, you can find that 4th bit. Don't let the math drive you crazy. You know this. Let's take a look at some visual representations here. So if 2 standard deviations from the mean correspond to a 6-point distance, right, then 1 standard deviation equals 3 points. And if you keep going, 3 standard deviations would then be 9 points. Because again, if you're no deviation from the mean, you're 0 points. 1 standard deviation is 3, 2 is 6, well then 3 is 9. Visually it looks like this. Okay, so we know in this example here, the average score is 65. Okay, say they were running a track race and they're doing a little like clicker thing and I don't know, they measure it in 65 seconds. Okay, 65 seconds. And the standard deviation, that sigma, that again, that circle with a little curly Q on top, right, is 6 seconds. If I am 2 standard deviations below the mean, that's a good thing. Again, in statistics, below the mean doesn't always necessarily mean a bad thing. Having a negative z-score is not necessarily negative in the classical sense. If it's a track race, I hope to be faster than you. I hope that my time is less than yours, right? Less, negative, under. In this context, is actually a really good thing. I'm placing higher than you are. I'm getting a gold medal, you're getting the silver, right? Okay. So if you take a look at this data, if the average time to finish this distance is 65 seconds, and each standard deviation accounts for 3 seconds, and my z-score, or my raw score, is 59 seconds, that means I am 2 standard deviations below the mean, or my z equals -2. Okay, here's another one. The 12-point distance from 42 to 54 corresponds to 3 standard deviations. Okay, so take a look at the graph. Okay, so you find your center there, right? Find your 0. Okay, 0. Okay, what's my mean? Okay, I see my mean. I see 0. Okay. 12-point distance from 42 to 54. Okay, so this looks a little bit different, right? So now I'm starting at -1, or z equals -1. What's my standard deviation? Take a look. Can you see it? It's 4. It's not -4. It's just 4. Again, standard deviation is the distance, how far from, if you're walking home and you're trying to find the mean. Yes, I know we're starting on the negative end of the number line, but standard deviation is how far away from, distance-wise, from the mean. Okay. So standard deviation is 4. Okay. So if I'm starting at the raw score of 42, which is -1 standard deviation, or z equals -1, I can determine what the mean is. So take a look at where the other score they give you. 2 standard deviations above the mean, or z equals +2. So if I know that z equals +2 corresponds to the raw score of 54, and I also know that a raw score of 42 corresponds to a z-score of -1. Do you see it? I can pretty quickly figure out that the average for this data set is 46, that mu equals 46. Okay. I also want you to take a pause and just kind of look at this graph here, right? Okay, so you have the normal distribution. Do you see how the first line they have written there, mu, right down the dead center, -1, 1, -2, 2, right? And that's the z's. Right underneath that, they have the raw scores. You see how the raw scores line up directly underneath the corresponding z-scores? Implied, but not explicitly written, are all the other scores that qualify to kind of nestle in between those z-scores. Meaning, you know, if the average for this distribution is 46, and -1z, or z-score equaling -1, is 42, if you scored a 43, you would fit in that little gap right there between -1 and 0. Now, in coming lectures, I will show you how to calculate your exact z-score. Right now, graphically, intellectually, you know you fit somewhere in that space. You know you fit, what I give you, 43? you fit a little bit closer to 42 than 46, right? So if I was to give you a marker, you could like kind of guess where your X would be or where your score would be. There is an equation, and I will show you how to do it mathematically, how to find your exact z-score. So it's not going to be -1, but it's going to be close to -1, right? So it'd be like negative 8.2436 or whatever it is. Okay. We can also use the z-score to standardize a distribution. Every x value can be transformed into a z-score, like I just mentioned. And there is a table. It's called the unit normal table. And I have it in our material section, so you have access to it. Yes, theoretically it does go on to infinity. And no, I don't have the one that goes to infinity. Nobody has that one. I have the one that goes like to 3 or 3.5. Some characteristics of the z-score transformation. Exactly the same shape as the original distribution of scores. I'm going to go back up, right? The shape doesn't change. If you have the z-scores or the raw scores, same shape. Okay. The mean of the z-score distribution is always 0. Standard deviation always chunks in 1. 0, 1 standard deviation, 2 standard deviation, 3 standard deviation. If you're going on the negative side, 0. -1 standard deviation, -2 standard deviation, -3 standard deviation, right? The z-score distribution is sometimes called a standard distribution or a unit normal table or a z-table. Okay. So when you transfer a population of z-scores into a population of scores into z-scores, this is what we do. Okay, you see how on the left-hand side there, you have raw scores. You have the average score of 100, and you have standard deviation of 10, and so it goes 100, 110, 120, 130. And if you go negative, you go 100, 90, 80, right? Okay. And if you transform the raw scores into z-scores, you now just make it 0 for the middle. And now the standard deviation of 1. So 1, 2, and if you go negative, -1, -2. Again, the transformation doesn't change the shape. All we do is just transform whatever the average score is to a 0, and whatever the standard deviation is to 1. Okay. We do this for a couple reasons. Number one, it's easier mathematically to look at it like that. Okay. It makes it more uniform. It makes it more uniform. I don't know another word for uniform. Right? So it just makes it so we can talk about it. It also makes humans feel a little bit better about their scores, right? Okay. Just really quick about x-axis relabeling following the z-score transformation. So following a z-score transformation, the x-axis is relabeled into z-score units or chunks. Right? The distance now is equivalent to 1 point. So like I mentioned, if you scored if the average on this one is 100 and you scored 110, your z-score would be z equals positive 1.00. Rarely is it ever that clean though, right? It's lovely if it is, but it's rarely that clean. So normally what it looks like is your raw score is, 103 points, 103.4. Great. I can make that a z-score. And again, you can kind of look at that, and it's going to be in the orange area, and you can be like, well, it's not quite half, it's a little bit shy of half, and 103, we read about there was 103.4. Mathematically, I'm going to show you, and again, like I said in a coming lecture, how to calculate it. And so it's not going to quite be 0.5, right? It'll definitely be plus, so z equals plus 0.4. Okay. So what you're doing is you're converting that 10-point standard deviation into just 1. Okay. Again, we do this because it makes comparing scores between classes easier, between groups of people easier. right? It makes all scores comparable. Scores from different distributions can be converted to z-scores, and now these z-scores are considered standardized scores, which allows direct comparisons. Okay. The process of standardization is widely used in all disciplines, right? So statistics is one of those skills that business people use, real estate agents use, all science uses, art uses, math uses, even English and languages uses, right? So anytime you can standardize anything, it makes it so you can easily compare it. Okay, so the two heavy hitters we use in statistics is SAT scores and IQ. Okay, they're the ones that most people are familiar with, and it's easy because the numbers are clean. Okay, so the SAT has a mean or an average score of 500 with a standard deviation of 100. Okay, and it's across the country like that. IQ is also clean and easy with numbers, right? So the average IQ is a score of 100 with a standard deviation of 15, and this is across the world. When we standardize the distribution, it's got two steps. Number one, the original scores are transformed into z-scores, and the z-scores are transformed into a new score, a new x value. And in the second step, the specific mean and the standard deviations are attained. The reason we do this, specifically for SAT and ACT, is because of feelings. We don't want to give out SAT scores, IQ scores with negative numbers associated with it. One, it's way too honest, and two, it would make people feel bad, right? Because what we don't want to do is say things like, oh, what's your SAT score? If you got your SAT score back and it was negative 1.2, you would know immediately that you scored not just bad, but you scored well below the mean. Humans don't talk like that to each other. Okay. Same thing with IQ. You can't give someone back their IQ test results and be like, you're below average. No, we can't do that. Okay. So what we do is we give them a converted score, right? So we take the raw score, we standardize it, we convert it into a z-score, and then we give them a new score based on that converted or standardized score. So when we give you an IQ score of 87, 97, 103, most people really don't know what that means. But now you do, right? Because if I tell you Jimmy's IQ is 97, you go, oh, okay. What you know now is, yeah, he's basically average. He's a little bit below average, but I don't know, maybe he's makes up in other ways, right? Or if I tell you that Jimmy's IQ is 117, you go, what? Oh, okay. Okay. Right? And also because you know about tails, like the body of the distribution, the tails of the distribution, and how tight those tails start to come in at the very, very end. If someone verbally tells you they have an IQ score of 147, no, probably not. Statistically possible, absolutely. The probability of you running into somebody that verbally tells you that they have an IQ score of 147, really low. Like, I'd go out and play Powerball after that conversation because, I don't know, or watch for lightning to strike you afterwards because probably not. Okay. So how to create a standardized distribution. So visually it looks like this graph here, right? So if Joe originally has a score of 43 and the average score is 57, do you see how his original score places him below average? So you take the raw scores, you convert them to z-scores. So his z-score is -1. if for whatever reason you don't want to give him that full transparent identifier, -1, what you can do is you can then standardize it and give him a new score, right? So if Joe has an original score of 43, yields him a -1 z-score, his new standardized score can be 40, okay? We also do this with like kiddos, like in elementary school, whenever we give them, every state is different, but every state gives them, usually in second grade, and like a child IQ test to see who's going to be in gifted classes and who needs remediation. Now, again, every state calls it something different, but it's their version of gifted and their version of remediation. And as soon as I say it, they're going to say, oh, those are bad terms, and you shouldn't say those terms anymore because every year we change the terms. But that's what they're looking for. They're looking for the outliers. They're looking for, really they're looking for anybody 2 standard deviations above and 2 standard deviations below. And they'll never tell the child or the parent in negative or positive terms. But that's what they're looking for. So they'll give a score of 40, or really they'll give a score of 30 and 70. What you don't do is give the score of -2 and +2. Okay, so taking a look at looking ahead. So thinking back to the first lecture, we talked about inferential statistics and descriptive statistics. This is where the semester kind of turns a little bit, right? So inferential statistics are techniques that we use because we can use that information gathered from samples to then question populations. Okay, we did this experiment with this small group of people. Can we now place it for a greater population? Can we interpret our research results from 100 people, 1,000 people? And is it statistically significant enough? Is there a noticeably difference between this group of people that we're now going to push out to a larger group, or maybe even to the whole population? Okay, and one technique for noticing noticeable difference is by using z-scores. So, oh no, this is exciting. I think this is the part of the lecture series that you start to actually take a look at and see at when you run an experiment or you run an analysis or you're running a study and you go, I'm not just looking at descriptive statistics anymore. I'm looking at inferential statistics, and I'm looking at making changes on a large group of people based off data of a small group of people. And defining it through noticeable difference, the first way we can do that is through z-scores.